So this is our transfer function, general form. We did lots of this already. Okay, so basically I got this multiplier in front. I got all this stuff with the S taus and all that kind of stuff, right? So the S to the plus minus N, if it's a plus N, I have what? What do I call that? S to the N. If N's positive, what do I call that? Zeros where? Well, there's zeros. There's zeros at zero, right? Zeros at zero, I guess, is the location of them. Their frequency is zero. If that N is a negative number, if I have S to the negative 2, what do I have? Poles, and those poles are at zero. Okay. Zeros cause magnitudes to do what? What does zero ultimately cause the magnitude to do? Ultimately causes it to rise. Poles ultimately cause it to fall. All right. When they cause it to start to fall is at the location of the polar zero frequency. Okay. All right. So that's the basic idea. This is sort of the summary here in the notes, basically. So for a typical pole, when I say typical pole or typical zero, that means that they don't happen at zero, right? So for a pole, flat fall. For zero, flat rise. All right. If I have poles or zeros at the origin, I say see next slide. Basically, what do those do? They rise. If they're zeros, they rise. If they're poles, they fall. Okay. And the summary of everything here, I basically have the different types, all of the types that you could have, right? Which we are not going to include quadratic poles and quadratic zeros. Too much to think about, right? If I have a single pole or a single zero, this is sort of a summary of them. Now this graph from Zybooks also includes over there what happens with the frequency, or sorry, with the phase. I don't worry about the phase in this class. All right, phase is something to worry about in quadratics or something that we worry about in systems. All right, later on. It's a little more complicated than you guys are mostly ready for. All right, that's a summary of everything. All right, so the process I give 5 steps. Figure out where the poles and zeros are, then map those to what I call breakpoints. The poles and zeros are always going to be negative numbers or zero. Okay. The breakpoints are always going to be positive, and those are the frequencies where stuff happens, where changes happen. Okay. Put the transfer function in that standard form. That's the second step. And graph each one individually, each pole or zero individually. Then add them all up and then shift it based on that K value. All right, that's our 5 steps. So we're going to go through that with a couple of examples. And I'm going to start with this guy here, which I called example 2. All right, I've got R1 is 1K, R2 is 100K, and C is 1 microfarad. So just to help myself out, I'll put these in. This guy would be 10 to the what? 1 kilo ohm. 10 to the 3. 100K would be 10 to the 5. What's 1 microfarad? 10 to the negative 6, yeah. Okay. All right. So what I want to find is, because again, the H of S is not just a math problem, but basically it's somehow there's a real circuit that I build. All right. And so here's a real circuit. Okay. I want to figure out what the transfer function is going to be here. My transfer function, what do you think it's going to be? What's going to be my input, do you think? And what's going to be my output? V in and V out are going to be my input and output. I got an input voltage source. All right, I got an output voltage that comes out of this thing. All right, so let's figure out what that is. How would I do that in this case? Now, this is something that you might be asked to do on the exam. I haven't made up my mind whether I'm going to put Bode plots on the exam. If I do, it will be 1 and it will be easy. But my sense is that I'm going to have op amps, transfer functions, and just some other stuff from exam 3. Because really the stuff from exam 3 and the transfer functions, those are things that you really need to know going into the junior year. All right, the Bode plots you need to know as well, but it's good for me to spend more time on just circuit analysis. All right. So if you get into electronics 1, they're going to assume you know circuit analysis as soon as you jump into that. They're not going to, I mean, they're going to quiz you on it and stuff, but they're going to assume you know it. All right, so I want to hammer you on that. All right. So what do? How do I figure out the transfer function?
Golden rules.
Golden rules, right? So in this case, what are the golden rules? Well, what are they?
There's no current in the voltage.
No current, no current into these inputs. This is I plus, this is I minus. So I plus equals I minus equals 0. Now V plus and V minus, what do I know about those?
They're equal to 0 in this case.
Yeah, they're always equal to each other. And in this case, they're equal to 0 because V plus is 0, right? So V plus equals V minus. That's the statement. Again, it's not exactly true. V plus is approximately V minus. We always, all purposes here, we just assume they're exactly equal. Okay. All right. So what do I do now? Do nodal analysis. So what I would do is I'd say, all right, well, here and here, I'll write the voltages like that. I'll call this V1. I'll call this V2. And I'm going to define a current going that way. And I'm going to define a current going that way. Okay. So where do I do my nodal analysis? Call this I1. Call that I2.
Node right at negative on the
Node right at the negative on the op amp. So in reality, I have I1 going in. What current's coming out of that node? I2. And technically also I minus. What do we know about that? 0. So I1 equals I2. Okay. So what's I1? What's the voltage in that resistor R1 there? Vn over R1. So, just to be really clear, it's Vn minus 0 because there's 0 volts at that V minus terminal. Vn minus 0 over R1. And then what is I2? So it'd be V2 over, I'm going to say it this way, V2 over Z. And Z, I'm going to say, is what? My Z be here? The resistor and capacitor in parallel, right? I could write this out as basically two currents, but I got two impedances in parallel, so I don't need to. I'm going to say that I got R2 in parallel with 1 over SC. All right. Now, what I would do is I know what the answer to that is, but how would I approach that if I didn't know what the answer is? Yeah, I would say it's R2 times 1 over SC times over R2 over 1 plus SC, like that, and get a common denominator. Now, I can also do that if I wanted to, if you're not comfortable with that. It would be R2 plus 1 over SC to the minus 1 power. Right? Now, how would you approach that?
1 over R2 plus 1 over 1 over
Sorry. Yeah, I don't ever do it this way. You're right. 1 over R2 plus SC. There you go. Thank you. If I had a euro, I'd give it to you. 1 over R2 plus SC, all that to the negative 1 power. So what do I do with that? Yeah, what is common denominator? R2. So I'd multiply the SC by R2 over R2, right? And this whole thing would become R2 over 1 plus SC R2, like that. All right, I skipped a lot of steps of algebra there, but what you should see how to do that, right? I multiply SC by R2 over R2, all right, and it becomes that. Okay. All right, so all that said, I would plug that Z in there. I don't want to plug it in just yet. I define this as V2. V2 is the voltage across that parallel combination. Okay. How do I write that in terms of node voltages though? 0 minus V out, because 0 is the voltage of the plus terminal of that impedance, and V out is the node voltage at the minus terminal. So I say it's 0 minus V out over Z, like that. Okay. All right, so this becomes V out over V in. If you do the algebraic manipulation, it's become minus Z over R1. Okay, that's my transfer function. That would be my H of S. And if I plug in, excuse me, all the good stuff here, I would end up minus R2 over R1 times 1 plus SCR2 like that. Okay, that's what that would become. Questions about what I did there? Probably are. All right. If I plug in the values of that whole thing, I would have ended up with H of S is negative 100 over 1 plus SCR2, which is 0.1 S. And let me just check that. R2 is 10 to the 5th. C is 10 to the negative 6. R times C is 10 to the negative 1. So I get that. Okay. All right. Now I'm at step 1. Okay. So this is what we would typically do. So that circuit gives me that transfer function. All right. Now what do I do? Step 1, determine the pole 1, 0 location. So what do I have here? One pole. All right, so I have no zeros. So zeros, I have none. And poles, what do I have? 1 at negative 10, right? So I say 1 plus 0.1 S equals 0. That corresponds to an S equal to negative 10. All right, so my pole is over here at S equal to negative 10. Negative 10 sits on the real axis right there. That's why, and I make an X for my pole, and I make a 0 for my zeros, but I don't have any to worry. Okay. All right, now I have this step 1A. I go, that's 1A. So basically what I do is I say I got no zeros, so none. And I have a pole at negative 10. What I do is I then relate those to the breakpoints on the Bode plot. Okay. So there is a pole breakpoint. That's what I write as omega P1. That is at 10 radians per second. If the pole is at negative 10, the breakpoint's at 10. All right. And I don't have any 0 breakpoints. 10 rads per second. If I were to give you a Bode plot on the exam, it probably would be something on this order of magnitude, like a single pole or a single 0 sort of thing. Or maybe 1 pole, 1 0 or something like that. Okay. Nothing like the example, next example I do is going to have a bunch of poles and zeros. It's going to be a party. All right. So, all right. Questions about up to here? Okay. All right. Step 2 is I got to get this guy in standard form. All right. So what did I end up with for my standard form? I was pretty close to it. Actually, I think I'm in it. H of S that I ended up deriving was negative 100 over 0.1 S plus 1, like that. Okay. So is that in standard form? It is. Okay. There's nothing. In other words, it doesn't have to have S to the power of something. It doesn't have to have any tau. It doesn't have to have that stuff, right? So, it could have, in this case, I've got tau Z1 equal to 0 and tau Z2 equal to 0. And there's not, and N is equal to 0. All right. So this is what I've got. So what do I have here? I've got a pole and a gain K, a multiplier K. What's K equal to here? K is negative 100. Okay. And I've got a tau P1. What's that? The first pole, what's my tau P1? Yeah, 0.1 or 10 to the negative 1, right? This guy corresponds to the breakpoint at 1 over 0.1 or 10. Okay. All right. So what do I do? Step 3. Generate a plot for each individual pole and 0 moving left or right on the frequency axis. So let's do that. Now, to begin with, I got to label up the axes. We just did this not too long ago in lecture. Where do I start with this, right? I got my little table here to help me, right? So omega equal 0.1, the log of that is -1. Omega equal to 1, the log of 1 is 0. Omega equal to 10, the log of 10 is 1. The log of 100 is 2. The log of 1,000 is 3, right? So I've got that. So what does that, how does that help me here in labeling these axes? What do I, yeah, so how do I label up my x-axis then? Where would I, where the two axes cross, that's the origin, 0, 0. So what frequency is here at 0? So I'll say I got 0 on the linear scale, 0, 1, 2, 3, 4, 5, 6, 7. All right, and this would be -1. What frequencies correspond to those values on the linear scale go from -1 to 7? What frequencies go from -1 to 7? What's -1 correspond to?
0.1,
Yep.
1, 10, 100.
Yep. 0.1, 1, 10, 100, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, 10 to the seventh. Now, what about going up and down on the y-axis? Well, it's the same thing, right? I'm doing log of 1 is 0. Log of 10 is 1. Log of 100 is there. But I multiply those things by 20, right? So this here is 20. This is 40. This is 60. What those correspond to right there, right? So 60 equals 20 log 10 of what? 20 log 10 of 10 to the third, right? 40 is equal to 20 log 10 of 10 squared, right? So what I'm doing as I go up the x-axis is I'm still going up by a factor of 10 each time, but I have that multiplied by 20. It just, again, it's decibels, right? It's not my choice that we do that, but that's what we do, okay? What about on the bottom side there? This would be what here? It corresponds to a value of -10 that I multiply that by 20, so it becomes -20, -40, -60, -80, -100, -120, like that. Okay, all right. All right, so I'm going to go so I can change colors here. All right, I want to draw them. I've only got one to draw here. The transfer function, probably just to remind ourselves, was h of s equal to -100 over 0.1 s plus 1. So I only have one pole to deal with. What happens with a pole? So in this case, eventually it's going to go down, but as I go left to right, where does he start? Starts at flat at 0 dB, and then he falls. So where does he start falling in this case? Where was the pole located? 10. All right. The pole is at 10. So he's going to be flat up until where? Yeah. So 1 on the linear scale, 10 on the log scale. So he's going to be flat to here. And then how fast does he fall? 20 dB per decade. So he's going to start falling at 10. And then when I get to 100 here, he's going to be at -20. And then he's going to be at -40. And then he's going to be at -60. And then he's going to be -80, like that. So it's going to go that way. Okay. That's what that guy does. That's all we have in this case. That's the whole Bodie plot. One exception. So step 4, I add them all up. So step 4, nothing to do for this one. But I do have a step 5, right? Step 5 is shift the whole thing up or down based on a K value. So what I had was h of s equal to negative 100 over 0.1 s plus 1, like that. Okay. All right. So what does the negative 100 do? In this case, I had 20 log 10 of, is the 20 log 10 a negative 100? 20 log 10 of the magnitude of that, right? Because what we're talking about is 20 log 10 of all of the magnitudes. So the downstairs would be 0.1 omega squared, like that. That's the magnitude of 0.1 s plus 1. All right. So what happens to the negative? I take the absolute value of negative 100, what do I get? 100, right? What effect does the negative sign have? Tells me the angle. If I looked at this thing, if I said the angle of h of s, it would be the angle of negative 100 minus the angle of the bottom, right? The angle of negative 100 is what? 180. All right, so the negative sign comes in the angle. So we don't need to worry about it since we're not worried about angle. But if I said this guy here, 20 log 10 of 100, or 10 squared, what does that equal to? 20 log 10 of 10 squared, 40. All right. So what does that mean? So step 5 is, because it's added like this, okay? Because it's added, we shift it. It just causes the graph that I drew in step 4 to shift up or down. So in this case, how much do I shift it up? 40 dB. All right, so I'm gonna switch colors to purple is always gonna be my second one, I guess. All right. How would I draw this graph here? What would I do? Take every data point and add 40 to it. So basically shift the whole thing up. So I'd start out here. And then I'd begin to fall. Where would I be at 100? I'd be at 20. By the time I got to 1,000, I'd be here. Basically the same graph, just sort of shifted around like that. So this is the complete graph. Okay. All right, so I'm gonna insert a slide here. Because I want to do an example again. So I want to say, well, where would I use this thing? So let's say V in was equal to 3 plus 10 cosine 2000 t, like that. All right, so I want to figure out the amplitude at the two frequencies that are here. So what are the two frequencies that are here? Yeah, what's the question?
When we shift the count to K, do we only shift the pole?
Do you shift what?
We only shift the pole.
No, you shift the whole graph. In this case, the graph is only one pole, right? But if I had two poles, I'd add them up and then I'd shift the whole thing. That's what we did in lecture, and that's what we'll do in the next example too. Okay. Yeah, this one's confusing because it just has the one. Okay. All right, so I got this guy, and I want to shift back to black. All right, so V in is 3 plus 10 cosine 2000 t. So this is the two sine waves, isn't it? What are the two sine waves? What frequencies do they have? 0 and 2000. Okay. This guy is DC, so his frequency is omega equal to 0. His frequency is omega equal to 2000. Okay. So I want to figure out the amplitude of the output at those two frequencies. So what would it be at omega equal to 0? Well, I go to the graph. Where is omega equal to 0? In this case, maybe you get lucky and say it's right along the y-axis. Is it right along the y-axis? Is that where omega equals 0? What is the y-axis here? What value, what frequency corresponds to where that x-axis is located? 1. Where's 0 on the log scale? Negative infinity, all the way off to the left, wherever that is. All right, so what is the what's the value of the magnitude of H at that point? According to this. At omega equal to 0, what's the magnitude of H according to this? 40 dB, all right? So according to this guy, the magnitude there is 40. So I would say that the magnitude of H of J0 is 40 dB. Okay. So if I want to figure out, and I got to be careful, the magnitude we say on the log scale, 20 log of the magnitude is 40 dB. So if I want to figure out what is the actual magnitude, what do I got to do? I got to undo that 20 log stuff, right? So what's the first thing I got to do? Well, I got to divide both sides by 20. So what happens if I divide both sides by 20? No, on the left side, I get rid of the 20. On the right side, what do I get? 2, right? 40 divided by 20 is 2. So what's the magnitude of, how do I undo the magnitude? Well, I raise both sides to the power of 10. So I say the magnitude H of J0 is equal to what? 100. So what that says is that the amplitude of the output at DC would be what? Be 3 times 100, or 300 volts. All right, now, if I built a real op amp, I wouldn't get 300 volts out, but let's just pretend I did. Right? You never built one anyway, so you don't know. Right? It wouldn't work like that. I should have just chosen a smaller number. Either way, that's the theory of what this says it would do. Okay. Now, I could also see that by just, if I look at the transfer function, I could plug in S equal to 0, right? And I should get the same thing. If I plugged in S equal to 0, what would that equal? Negative 100. Well, wait a minute. So this is saying it's negative 100. I just said it was 100. Magnitude, right? So what it's saying is if I put 3 volts DC in, I would get negative 300 volts out. The magnitude of what I would get out would still be 300, right? But it has a phase shift of 180 degrees, right? All right. What about at 2000 radians per second? What's the magnitude there on the log scale? All right, so I chose a weird one. Where is 2000? Previously, I chose stuff that's right on the tens, right? So it was nice and easy to figure out. Where would it be? Here.
Would it be the next vertical line over?
It would be, yeah. You notice this, it's kind of goofy. Like what happens is, as you look, the vertical lines are spaced funny. So there's a big gap between 10 and 20. There's a smaller gap between 20 and 30. There's a smaller gap between 30 and 40, smaller between 40 and 50, and it just gets smaller and smaller and smaller. You don't need to worry about that so much, right? What I'm gonna do is I'm gonna say it's linear here, right? It's basically, it's linear in that range. So if I looked at this, all right, so let's look at the complete graph. Well, I said 10, what did I say, 20,000? No, not 20,000, 2,000. Where's 2,000 here? And it's between 10 cubed and 10 to the 4th, right? Now, I could eyeball this, and that may be what you do. I probably would say, I could look at this and say, what's the slope of that graph? It's linear in that region, right? What's the slope of it? Negative 20 dB per decade. So here's what I would do. Where am I? What's the value at 10 to the 3rd? 0. So if I want to figure out what it was there, what I probably would do is I would say 0 minus 20. And I've gone. How would I do this? So this what I would say is there's a couple of ways I could do this. I would say But what I'm trying to do here is I'm trying to write an equation for that line, right? I know that it's linear and I want to plug in the value at that particular point. And I want to do that. I want to be lazy and not write the full equation of that line. Remember, how do I write an equation of a line? I need to know its slope. I know its slope. What else do I need to know? It's y-intercept. So what is the y-intercept of that line? If I drew it back, it would be 60, right? So if I wanted to be exact, I was trying to come up with another way to do it, but what I could say is that line, the equation of this line right here, if I wanted to do that, is 60 minus 20 log 10 of omega, right? Where this is like my x variable, like that, right? So I can think of it like that. You guys with me on that? All right. So what I can say is y equals 60 minus 20 log 10 of omega. And I could plug in log 10 of what? I would put in 2000. So 2000 like that, right? And I could solve for what the y value was. The y value would be the magnitude at that point. Okay. Now, that should hopefully be straightforward to try to figure out here. That's what I would do. What I know without me trying to go through that math, what I know is that approximately, if I looked at that point, like going from 1,000 to 2,000 is going a third of a decade. So I'm gonna just eyeball that. Oh boy, I'm gonna just eyeball that and say I went a third of a decade. So if I went a third of a decade, you guys, all right, let me not try to approximate this. All right. What I would do is I would solve for this to get whatever that answer is. So let's just go to MATLAB and do it. All right. Because that's what you should do. Don't try to come up with some trick like I'm trying to do. All right. So let me move this off to the side here. So 60 minus 20 log 10 of 2000. So what would I do? I made it go away. All right. So I would say 60 minus log, so 20 times. Now here's a key thing. I always write log base 10. You're probably used to writing log base 10 as log log. All right. I lost a couple of hours of my life back when I was in college, not realizing that log in MATLAB, if you write log, it's natural log. It's ln. All right. So if you use this, you could be like me and you could lose hours trying to figure out why MATLAB can't do this. In MATLAB, it's log 10. Okay. So I do log 10 of 2000 like that. All right. And I'm going to end up with negative 6.0206. So this guy here is negative 6.0206. That's equal to 20 log 10 of the magnitude of h of j 2000. Like that. Okay. So if I want to undo that, I would say that the magnitude of h of j 2000 is equal to what? It's 10 to the minus 6.0206 divided by 20, like that. All right, whatever that works out to be. If I did that math, it would be 10 to the, I would write this as ants divided by 20. So ants is answer, so it'd be 0.5. Okay, this is 0.5. So that tells me that what would be the amplitude of the output at 2000 radians per second? It would be, yeah, it'd be 5. Now, in reality, I mean, I don't ever use a Bodie plot like that where I go and say, well, I'm gonna pick some weird number like 2,486, right? I wouldn't do that. If I really needed to know that number, I would go to MATLAB and just graph the Bodie plot and do it that way. All right. The Bodie plot's a useful tool for design. It helps me think through the stuff. All right. And it's important to know how to do it. We use them a lot. All right. But I would never, in practice, I would never do what I just did and approximate it as a line. That said, I will test you on that because I want you to understand the concept. Okay. All right. Questions about what I just did here? All right. I got another example here. So how are we doing on time? Doing all right. All right. So skipping through all this stuff here. All right. This was our process. Let's say I got Mr. Ugly here. All right. So Mr. Ugly, I got h of s is -10 times s to the 0.1 times s plus 100 over s squared over s plus 2000. Is that in my standard form? Certainly not. He's ugly. He's going to get uglier as I go through. All right. But what I want to do is I want to figure out with this character, where are my poles and where are my zeros? So what did I say? I had h of s is -10. And then I had s plus 0.1, s plus 100. I got an s squared, that's ugly. And then I got an s plus a 2000. Like that. Okay, so what do I do? Poles and zeros, first step. Okay, so what are my poles and what are my zeros? I got a pole at -2000 and I have two poles at 0. All right. Now the fact that I have two matters. Okay. So I have poles at 0, 0, and -2000. That's weird to say 0, 0, and -2000, but there's a reason why I'm saying that. If you told me on a test 0 and -2000, no, full credit, right? I wouldn't say write it like that. But there's a reason why I'm splitting it out that way. Because I got a double pole there. Zeros. What are my zeros? Well, so yeah, s equal to -0.1 and -100. Okay. And then I could draw X's and O's at those points. I'm not going to do that. I just want to know where the poles are at. Okay. Okay, so I want to figure out the breakpoints. So my poles were at 0 and 0, and at, why can't I remember? -2000. And then these guys are at -0.1 and -100, right? Okay. All right. So what breakpoints does that give me? Yeah, it gives me breakpoints. It gives me a breakpoint at 0 on the pole side and at 2000 on the pole side. And at what on the 0 side? What would be my breakpoints for the zeros? It'd be 0.1 and what? 100. All right, so I've got those guys there as my breakpoints. All right. So what do I do next? Well, I go to step 2. What is step 2? Get it in standard form. So yeah, what do I do with that? How do I get that into my standard form? Fortunately, I copied that over for myself. It's doing some glitchy on me. All right. How do I get that in my standard form?
You multiply the first term by 10.
Well, I don't multiply things by 10. Well, I know where you're going. I pull the 0.1 out of this first term here. Okay. I pull the 100 out of this guy. I pulled the 2000 out of here. Okay. So if I pulled the 0.1 out, this would be -10, and then what happens there when I pull the 0.1 out? So I have, I'm gonna say 10 to the -1 times, what happens to the s plus 0.1? Be 10s plus 1. And then I also need to pull out a 100. So I would say a 10 squared comes out. And then what's this guy become? It's gonna be s over 100 plus 1. And then down here, what happens on the downstairs? Pull out 2000, so 2 times 10 to the third times what? S over 2000 plus 1 times s squared. I commuted. Okay. All right, so what I'm gonna do is I got a k value clearly. So how do I get that? I got 10 times 10 to the -1 times 10 squared divided by 10 to the third. So what is that? I can just count up the exponents, right? I got 10 to the 1. So 1 minus 1 is 0 times plus 2 divided by 3. So that would be what? That would be 1 minus 1 is 0, plus 2 is 2, minus 3 is -1, right? So it would be, yeah, 1 over 2 times 10, right? Is what I end up with. And then, huh? No, the negative sign stays there. The negative sign stays there, so I get a -1. So a -10 s plus 1 times s over 100 plus 1, and then s over 2000 plus 1 times s squared. Okay, so instead of writing 2 times 10, it doesn't like my erasing when I'm in this mode. All right, so it's, what's 2 times 10 is 20, right? So it would be 2, that looks ugly to say 2x10. But that's my transfer function in my standard form. All right, so what do I do next? What's step 3? Graphing, okay. So I got to graph this guy. So in terms of my graphing, oh boy. Let's try to go to slideshow mode here. See if that fixes this. Okay. Yeah, okay. I'm testing the memory here on my computer. All right, so let's. All right. Oh boy, I don't know what it is. H of S. Oh boy. H of S. Oh boy. All right, don't do this to me. H of S is equal to, oh boy, 10s plus 1 s over 100 plus 1 s squared. There's a negative sign here, and s over 2000 plus 1. And I got a 20 on the bottom. Did I write that wrong? Oh boy, I don't want to tempt fate here. Okay. Did I write that wrong? Did you write it down? I think I was right. Looks right. All right. If it is, we'll learn something even if I do the wrong one. All right. So what do I do here? What do I do? I cry a lot. Probably a good idea, right? So step 3, what is step 3? Do a plot for each one. Step 4 is add them all together. What do I do? Where should I start? Give me a choice? Well, I probably should label up these axes, right? That's always helpful. So, all right. So labeling up my axes. This I say I got 0, 1, 2, 3, 4, 5, 6. -1, -2. What frequencies do those correspond to? Moving left to right, as I go from -2 to 6. What frequencies do I have? Yeah, I got 10 to the -2, 10 to the -1, 1, 10, 100, 1,000, 10,000, 100,000, 1 million. Now, going up and down the x-axis, sorry, the y-axis, I got 0, 20, 40, 60, 80. Going down, I got -20, -40, -60, -80, -100, like that. Okay, so I got my axes all labeled up. Who should I start with? Well, yeah, so my breakpoints that we identified here, so I said that I got an omega p term at 0, and I actually had 2 poles there at 0, and I also had one at 2,000, at 1 over the tau value. And I had zeros at 0.1 and 100. All right. So where is the pole at 0? Well, that's the s squared, right? Where's the pole at 2,000? Well, that's the s over 2,000. Where's the 0 at 0.1? That's the 10s, right? The s times 0.02, or sorry, 0.01, so the s over 100, that's the pole at 100. Sorry, the 0 at 100. The 0 at 100. S over 100 plus 1 is the 0 at 100. All right, so let's go through. Let's start at the top. Let's go clockwise here, I guess. So I'll start 10s plus 1. That's a 0, and it's a 0 located at 0.1. So what do I do for that, moving left to right? It's going to be flat, and then it's going to do what? Go up. Where does it start to go up? 10 to the -1. So that would be at -1. This guy's going to be flat, and he's going to rise up like this. Okay, like that. Okay. All right. That is, so let's just be, I'll label them up later. I'll make sure I don't overlap too much. So I got another 0. So moving clockwise, the next 0 is at 100. Okay. What do I do for that guy? Flat until 100. Flat until 100. And then I start to rise. So he's going to rise like this. Okay. So, all right. Then what? What's next? Now I'm moving clockwise. Then I get to that S over 2,000 plus 1. That's a pole. And it's a pole where? At 2,000. Where's that? Yeah, in between. So that's that first tick there between 10 to the 3rd and 10 to the 4th. So what am I going to do for that guy? Flat until 2,000. It'll be flat to 2,000. And then I'm going to fall. And what rate do I fall at? Same rate as all the others, 20 dB per decade. So, all right, that means that at 20,000, I would be at -20. And at 200,000, I would be at -40. And at at 2 million, I would be over there. Sorry, 2 million, I'd be over there at -60. So I draw this guy like this. Oh boy. Be like that. Okay. Eventually, I'd add all those up. Okay. Now, I got one more thing to do. I got s squared. But that's a little tricky to do, right? What is, if I have just an S term, if I have a pole at zero, what do we say a pole at zero does? Always falls, okay? So what would happen if I had two of those? It falls twice as fast, has twice the slope. So if it falls twice as fast, it would fall 40 dB per decade. So in other words, he would start here. So I know he's going to pass through zero. Right? At -1, he would be at 40. At -2, he would be at 80. And he would fall twice as fast. All right. So here, so he would look like this. He would go. He'd fall like this. All right. Now I gotta add all that stuff up. It's gonna suck, isn't it? All right. So what's that gonna look like? So step 4 is I go from left to right. This is about as hard as it would get. All right. So let's go from left to right here. As I go from left to right, I'm going to start at -2 because that's where my graph starts, right? Basically, the way that I look at this is as I move from left to right, I look at how many poles or zeros are active. That's the way my brain thinks about this. What do I mean by active? I mean, how many poles and zeros are rising or falling at that point? Because anything that's not rising or falling at that point, how much does it add? 0, right? So I look at basically how many are active. So the only one that's active are the two poles at 0. So the total graph, and I really want to use another color. I have no idea how I would do that without going back to my, I don't want to tempt fate and go back. So where's it going to start? It's going to start here, right? It's going to follow this guy. He's going to follow that guy into what point? When does something start to get active? Point 1. What happens at point 1? I come across a 0. So I was falling at, so what's the rate that I'm falling here in this region? This guy's -40 dB per decade. At point 1, I hit a 0. A 0 causes me to rise at 20 dB per decade. So what's the net result of, so I'm adding something that's making me fall at -40, and I'm adding something that's trying to make me rise at 20. What do you think is going to happen? I'm going to fall at -20. So my slope went from -40, I added 20, -40 plus 20 is -20. So what's going to happen is he's going to shallow off. He's still going to be falling, but he's going to shallow out. So the way I would do this is I'd say, all right, well, at that point, 0.1 is when that happens. So what I'm going to do is I'm going to say the summation starts to look like that. He starts falling at 20 dB per decade. And so I keep it going at 20 dB per decade. So here, multiple colors would really be good. Okay, you guys with me? The total graph is the total graph. I'll thicken it, I guess, a little bit. This is the total graph. That's just going to make it worse. All right. Total, well, I'll label it up somehow at the end. Now I stopped there at 10 squared. I stopped at 100. What do I have at 100? I have another 0 that comes in. And that 0 causes me to rise at 20 dB per decade. So right now, the overall graph is falling at -20. And then I come across a 0 that makes me want to rise at 20. So I'm falling at 20. 0 makes me want to rise at 20. What's the net result? It's going to flatten off. He's going to be at 0 dB per decade until he comes across to 2000. At 2000, he comes across what? He comes across a pole. That pole says fall at 20 dB per decade. So the net effect is that now I'm falling at 20 dB per decade. So I'd start here, and then I would start to fall. Oh boy. At 20 dB per decade. like that. Okay. So let's label these up. This guy here is the but I want to be careful. This is the poles at 0. This guy is the pole at 2000. This guy is the 0 at 100. And this character is the 0 at 0.1. Yeah. Yes, sir.
I lost your, that you just.
I appreciate your honesty. That was good. Everybody did. I'm glad you were honest about it. All right. What part did you lose me?
Which combine.
That's the hardest part, right? Is what I'm doing, and it's a great question, because this is the hardest part, right? Is as I move from left to right, I figure out where does the graph start at the left. And then I basically just count how many poles or zeros are active in that range I'm in. Okay, so what I do is I'm starting out here and I'm saying, all right, at this point, the only thing that's actually causing me to rise or fall are the two poles at the origin, the two poles at 0. So at this point, I'm falling at negative 40 dB. And I've been falling at negative 40 dB since the dawn of time, all the way out since negative infinity. All right. When I reach 10 to the minus 1, at that point, I reach a 0. And what's happening at that point is I'm saying that I've got, maybe this is the way to think about this. Is I'm gonna break the frequency range up, and I'm gonna say for omega less than 10 to the minus 1, from 10 to the minus 1 to, where's the next one? At 100. And then from 100 to 2000. And then from 2000, say for omega greater than 2000. Okay. Those are the ranges in between my breakpoints. Okay. So for everything less than 10 to the minus 1, then between 10 to the minus 1 and 100, and then between 100 and 2000 and everything greater than 2000. What I did there is I just defined out the breakpoints. You with me on that? Okay. What I'm going to do is I'm going to say how many poles or zeros are active. How many poles as I move from left to right? So I use this active, or how many have I hit, right? So as I go from left to right, if the frequency is less than 10 to the minus 1, I have 2 poles. Okay. Once I get to 10 to the minus 1, I have 2 poles and 1 0. You with me on that? Yeah, I got 2 poles and 1 0. 2 poles plus 1 0.
That's the dual are still 2.1.
Yep, that's right. Then when I get to 100, I hit another 0. So at that point, I've got 2 poles and 2 zeros. I'm glad you asked this question. This is a good question. All right. What about from omega greater than 2000? At that point, I've got 3 poles and 2 zeros. Okay. You with me? So there's 2 poles here at 0. That's the S squared. The third pole is at 2000.
Oh,
Okay. So the way I kind of look at this is I know that it's either rising or falling linearly between these ranges. Okay. So if I have 2 poles, I'm falling at negative 40 where am I gonna write this? I'm gonna write this over here. My slope here would be negative 40 dB per decade. 2 poles, it's making me fall at negative 40 dB per decade. If I combine 2 poles and 1 0, I got minus 40 plus 20. So my slope would be negative 20. In here, 2 poles, 2 zeros. The poles, and the way to think of it, each pole is giving me negative 20. Each zero is giving me positive 20. So I got minus 20, plus 20, plus 20 is 0. Slope wise, I can think of it that way. This guy would be 0 dB per decade. What's that?
That's why it's gonna be. flat.
That's why it's going to be flat, because it's a line with the slope of 0 dB per decade, right? And then here I got 3 poles, 2 zeros. So what do I have? 20 plus 20 plus 20, minus 20, minus 20. So I'm going to be minus 20 dB per decade. That's the way that I actually think about this in my head, is I mentally kind of bracket it out and I look at each of those ranges like that. Okay. You guys with me on that? All right, now the one problem yet. Step 5. What's step 5? Yeah, I get that stupid 1 over 20. All right, what's 20 log of 1/20th? I should show some better numbers. Somebody tell me. I don't want to get out of this thing. 20. What is it?
Yes.
Take a guess. Don't take a guess. Let's see. Let me see. I'll go to my calculator. 20 log of 1/20th. 20. So 20, yeah, 20 log of 1 over 20. Negative 26. All right. So what do I got to do? So if basically what it's saying for step 5, I got 20 log 10 of 1/20th is equal to negative 26. What do I do? Pull everything down by negative 26. Okay. So I would shift this graph here down by negative 26. Okay. So where would I start with that? I guess I would probably start right here. And I'd take this guy, which is at negative 20, and I would take him to negative 46, where that would probably be somewhere around here-ish. And we look something like that. And then something like that. So I wanted multiple colors. All right. This would be the final. There. All right. When I post this to Canvas, I'll post it with multiple colors. All right, so you guys can see it that way. All right. All right. Now, again, I think, where am I at on time? I got 2 minutes. I won't do anything further, but I'll stop there.